Welcome to NOAA Live. We are so glad to be back. My name is Grace Simpkins, and I'm going to be moderating today's webinar. This series is sponsored by NOAA's Regional Collaboration Network, which is spread across the country and helps connect people to all that NOAA does. It's also sponsored by Woods Hole Sea Grant, where I work, which is located at the Woods Hole Oceanographic Institution here on Cape Cod. NOAA Live webinars will be offered most Wednesdays during the school year at 4 p.m. Eastern Time. And to get more information, you just have to log on to the Woods Hole Sea Grant Education webpage, or you can follow us on Facebook, Twitter, or Instagram. This series is designed to help you get to know NOAA and some of our incredible experts. All of our speakers work for some part of NOAA, and if you don't know what NOAA stands for, we are the National Oceanic and Atmospheric Administration. Today, it is my pleasure to be introducing you to Frank Niepold and Tom Liberto, both with NOAA's Climate Program Office in Silver Spring, Maryland. Now, they have a really exciting talk because I've seen it, but while we'll be talking about NOAA's research on carbon's journey and our warming planet, first we want to recognize that we are all coming to you from the traditional lands of Native communities who have substantial traditional and local knowledge and much to share with us. We acknowledge that Frank and Tom are coming to us from the land of the Piscataway Conoy tribe and the Piscataway Indian Nation. We are hosting this webinar from the ancestral lands of the Mashpee Wampanoag tribe and the Wampanoag tribe of Gayhead-Aquina. A few guidelines before I hand it over to Frank and Tom. I know you're eager to hear what they have to share. You are all muted as normal. We have a lot of people on the line. We want to make sure that you can hear Tom and Frank. However, there's a box, the same box where you wrote where you're from. You can write your questions. We encourage you, we want questions. So please write them as we go along. I'll keep track, and Tom and Frank will stop every now and then and answer a few. We might not get to all of them, but we'll get to as many as we can. Now, enough of me talking. I've talked enough. I'm going to, at this point, turn it over to Frank and Tom, and I will turn off my camera. All right, it's all yours.
Grace, awesome. Thank you so very much. Are you still seeing the screen, or did that just go away?
So your PowerPoint went away. We're just seeing your background, which is a beautiful, looks like an island. So we've lost your
yes.
PowerPoint.
I'm not sure where that went to. So let's try and get that back. That's a strange little fun thing that technology decided to do. There we go.
Perfect.
You're seeing it again? All right. Well, so nice to be with you. So when we accepted this offer, this wonderful offer, the model that you guys are using here was to just share a little bit about us. So, this is a picture of me. It's summer camp back when I was in 6th grade. So there are people, students with us today that are of that age or younger. I'm a little older than Tom, so my picture's with black and white. Tom, is that a picture of you?
That is a picture of me. I'm the one who's not the dog. That is me. That's my dog George. I got my dog George on my birthday when I started 6th grade, because I just started middle school and I was having some tough times with it. So my parents were like, I'd been begging my parents for a dog for a very long time, and they got me my dog. That's my dog George. So yeah, a little bit different between your black and white. Still very nice, Frank. And then my photo of me at the beginning of I was 11 years old in this photo.
Yep. And by the way, I have a dog named George as well. Funny to know. He's downstairs barking. So hopefully, if you hear that, you might even see a little hint of George coming up. But it's exciting to be with you guys all. And one of the things that in this format, you guys, and I get this question a lot myself. And I'm the climate education coordinator and senior program manager for NOAA's Climate Program Office. So, how did I get interested in climate? Wow, that is an interesting question, and I struggle with it a little bit because it's been a wandery path, but it very clearly showed up for me back in the 90s when I was working at NASA. on something called Mission to Planet Earth. And when we were working on that, climate was becoming a stronger, important issue. And I was working on it, but more on Earth systems. And but then it just became clearer and clearer that climate and climate change were going to be a massive issue with great importance. And so you know, and that wasn't the priority for NASA at the time. And so I moved over to NOAA in 2005 and haven't looked back since. I was supposed to be here a year, and it's now 15 years later. So NOAA has a funny way of, once they get you, they keep you. So I work across the country, internationally, and work with people from almost every state, and on trying to figure out how to support you guys as learners. So that's part of my job and mandate, but clearly it's a really important topic, and I'm really happy to have colleagues like Tom. So Tom, how did you get interested in climate?
I have been obsessed with the sky since I was old enough to understand what the sky was. In third grade, this is a story. I always joke that my teachers always told my parents that I was quite a storyteller growing up, and I'm pretty sure it just meant that I never was quiet in class. But in third grade, the teacher, we were going through a lesson where they were asking us what we all wanted to be when we grew up. And in third grade, I said I wanted to be a meteorologist when I grew up.
Wow.
I've just kind of been obsessed with the weather since I can remember. Every science experiment I've ever done in school revolved around the atmosphere in some way, even when it didn't make sense. I still would just make my science experiment somehow related to the atmosphere. So, yeah, so my job, I think of myself almost like I'm a climate scientist at NOAA's climate program office, specifically with climate.gov. I run all their social media, I write articles, I do all sorts of things as it relates to communicating climate and climate science, and doing some climate science too. But my first love was always the weather, because I always wanted to know if there was going to be a winter storm that dropped snow on me, so I'd get a snow day. That's where it all came from. But I really got into climate as I got older. I found myself more interested in how things are changing. And I noticed how things were changing. I also noticed how things were changing when I talked to my parents and the weather they experienced growing up compared to what I was experiencing, and then all the science I was learning. So I eventually got really interested in climate, and I got more and more concerned about climate change and wanted to talk about that more for a career. So I've been at NOAA for 10 years now, but really only in the communication side of things for a couple of years. But there's one thing I'm always going to be talking about the sky no matter where I am, and that's for sure. Listen, I love clouds. I'll just be honest with you. Clouds are my favorite thing in the world. I absolutely love clouds. There's nothing wrong with that.
Nope, nothing wrong with that at all. You know, it's funny though, as you think about it, the picture of me that started this off, I always attribute my love of place and earth and environment to my time on the Eastern Shore at my summer camp when I was a kid, because I grew up in a downtown neighborhood in Philadelphia, and you know, there isn't too much nature there. But you know, I just got lost in the woods and streams and marshes, and literally when I was out there, and I loved it. So you know, I don't know where I got all this started from, but it started young, that's for sure. So let's get into it. The and you know, actually, I was thinking about this, Grace. If you wouldn't, if the students who are with us today, if they wouldn't mind chatting to you, we'll pick it up later when we get a break for some questions. What grade are they in? It would be really helpful for me to know what grade students are, because I was a middle school science teacher. I taught earth science in middle school, and I loved it. Sixth grade was my favorite. Of all the students, I've taught 6, 7, 9, 11, 12, some college, and sixth grade was always my favorite. So, and I've never taught anything younger, so maybe fifth is even better. Who knows? I didn't get there. So today we're going to be talking about how is carbon's changing journey warming our home. And so if you want to know something about this topic, feel free. Tom and I are here at your disposal and your service. But we're really looking at how carbon dioxide is working in the earth, and how is it changing, and how is the earth changing as a result. So so my open question to you is, on the earth at the planetary level, what pulls carbon dioxide, any form of carbon in the air? And let's remember, when you move your hand back and forth in front of you, right, you don't smell anything, you don't taste anything, you can't see anything, but you could feel air rushing around your hand as you move it back and forth. That's the air that makes up our atmosphere, that holds the clouds, the things that Tom loves. And in that air, there are gases, a whole mix of them, but the one that's really important from a climate perspective is actually carbon dioxide. And how much of that's in the air is really important. But there are things that on the earth that will move things from not in the air into the air, and then back from the air back into into the other places. So what do you think pulls carbon down from the air, removes it from the air? Any answers?
Okay, so this is Grace. I'm monitoring the chat box. So Frank just asked you, so don't forget, you can write your answers in the same box you've been writing things in. What pulls carbon dioxide? What removes it from the air and puts it back into the soil, or in some way removes it from the air? So we've got a series of answers. So Sloan in Texas think that, and Michelle think that it's gravity. Donna thinks that maybe it's plants. Clark thinks trees. Idia, I'm sorry if I'm mispronouncing that, trees and bushes. Sonia thinks maybe gravity and wind. Donna thinks the ocean surface. Connor and Daniel think moisture. We've got plants, algae, ocean, rain. So we've got a lot of different answers. And I'm going to pause there because I think that gives us a wide range of answers to work with.
Awesome. That is some great answers. And so here's a couple things that I put in there. We got soil, and soil is a really important part of this. But then you also have trees which are interacting with soil. And so I like this picture of seeing the roots. There's a lot of plant structure below the ground that has also got a lot of carbon in it. So it's both of these things. But let's not stop there. And remember, we're at NOAA, the National Oceanic Administration, and seaweeds themselves, and plant matter and other forms of activity that they pull life and energy from the sunlight. They're going on and doing this. But then also another important thing are these coastal plants like mangroves and marshes. They pull huge amounts of carbon from the atmosphere, and then also the ocean itself. So you guys got it. It's really those processes. Now gravity, not so much, but I get why you're going there, but it's really these processes that they're interacting with gases, either putting them back up or pulling them down. These are the ones that pull it down. These are the big ones. So those are those. So let's go over to the other side, not pulling it down, but releasing it back into the air. What releases carbon or carbon dioxide into the air? So Grace.
Okay, this is Grace reporting from the chat box. So Frank's question to you all is, what is releasing carbon dioxide back into the air? And so Paul and Alice are saying us. Sarah says animals and respiration. Michelle is saying plants. We're getting Sonia saying cars and other vehicles and people. We're getting quite a few humans. Ada and Carl are saying humans. Catherine says cars and factories. Donna says burning fossil fuels. So we've got, I'm seeing a lot of those same answers. So I think I'll let you go from there, but we've got a savvy crew today, Frank.
Oh, savvy indeed.
Mm-hmm.
So, so plants, absolutely. And plants themselves actually release carbon, not just, water vapor, but carbon back in the air. They breathe just like us. But one of the big ones that wasn't mentioned is volcanoes. And so these are more the natural processes that move carbon into the air, and we'll get to the other ones that were mentioned. But decomposers, that break down those plants are also going to be emitting carbon back into the air as part of their living process. Actually, weathering of rock releases carbon into the air is one of the other areas. And then the ocean itself also releases carbon back into the air. And that's a very big part of the process. So these are the natural processes before us. That's why I thought it'd be important to look at the ones with us and the ones without us first. So, did any questions pop up yet? I mean, we haven't really gotten into it, but I just wanted to check in if there's any questions about any of this that anybody wants to know before we get into kind of how this all works. Now, that would be good.
Okay, so this is Grace reporting from the chat box. I'm just first going to share with you, before I give you the questions, sort of the ages. We have a wide range. We have some second graders, fourth graders, fifth graders, sixth graders, and a seventh grader. And then Clark is a first grader who's very interested in science. So that's kind of the age range. But Katya is asking, does fire contribute to carbon dioxide being released back into the atmosphere?
Tom, you want to take that one?
Yes, it does. That's exactly right. When you light plants or any, does be trees, it could be grasses, it could be bushes, but when you light those on fire, you're releasing a lot more all at once carbon dioxide into the atmosphere.
One of the common ways we look at this is if you take a log that you're going to burn on a campfire, since we just finished the summer, and maybe some people are still doing campfires outside, except for out west. Don't do that. That log, all that mass, if you feel the weight of it, when you burn it, that weight is moving from a solid form into a gaseous form, into the air. That's where that mass is going. If you burn it all down and you just have ashes left, the mass that isn't in that ash is actually in the air. It doesn't disappear, it just moves from a solid form into a gaseous form or a gas, and that's how it works. And so this absolutely, and that's one of the big concerns we have with what's going on in the Western United States right now, is all those fires are transforming those forests into gas producers for carbon dioxide moving into the air, which is a problem. So, any other questions, Grace? It's a great
yes,
one.
this is great. Grace reporting. I have one more, and I want to thank Katya because that is very relevant today with the fires that are happening on the West Coast. One last question before you move on. If you could just tell us, Sonia asks, how does the ocean release carbon?
Ooh, Tom, do you want to do that one, or do you want me to?
You start, and I'll tag team in.
Sure. So there's when gases are in contact with a liquid, right? So imagine you have a glass of water and you have air above that, like you're in your room where you are. The gases are going to naturally move into the water, or they're going to move from the water out. And it depends on other factors like temperature as to how much gas is going to move one way or the other. It's a constant process. And so if you have a lot more of carbon dioxide in the air, it's naturally going to move into the water. And then if it has too much at one other time, it will move back out. So it moves back and forth across the water-air boundary. How'd I do, Tom?
That's exactly right. So when you have that top level of the ocean, you can have, it may seem like it's solid, right? When you go to a beach and you go into the water, you're going into water, right? But there's actually a transfer of gas that you can't see because it's so small at that top level of the atmosphere, and it's constantly ongoing. You can have gas come in, CO2 go in, and then lead to organic life like algae and phytoplankton. They can then use that carbon dioxide to produce oxygen. That's one way of doing it. But you can also have that gas come out when certain materials, nutrients, or animals or whatnot die in the atmosphere. It also can release the carbon dioxide out. So it may look solid, but there's a lot going on that you can't see with your eye.
Absolutely. And one of the other important parts of that is once it goes into the top of the ocean, it can either stay there or it can move down deeper into the ocean, sometimes all the way to the bottom. And that we at NOAA, we measure all of this stuff. We measure how much gas is above the atmosphere, in the atmosphere. We measure how much is moving from the atmosphere into the ocean, how much is moving through the ocean. And then whether it's temperature or gases or all of it, because the only way we can answer these questions is if we've done the work, we have the data, and we have the people, maybe some of you in the future, who actually continue to do this work, because this is work that people have been doing for hundreds of years. And it only builds more and more understanding of our wonderful, complicated planet that we call home. So let's get into it. Is that all right, Grace?
That is perfect.
Awesome. So who knows what a fossil fuel is? Sorry,
All right,
questions.
Grace reporting from the chat box. No, questions are great because this keeps you on your toes. You might think by watching this webinar that you can just snooze over there, but you can't. So I want all the kids to report in. What is a fossil fuel? Maybe you can give us an example of a fossil fuel. Let's see, who's got an answer for us? So Michelle says that coal. Sloan says it's fuel made of fossils. Clark says oil. We've got Ada and Carl, they're saying coal as well. So we've got coal and oil. Oh, Donna says gasoline. And Sonia thinks maybe it's carbon dioxide and other fuels emitted by humans. Mm-hmm. We have a bunch of coal, gas, and oil. Yeah, and a lot of people think that it's from fossils or dead animals. And Texas and Nicole are wondering if natural gas is a fossil fuel. So, oh, and then I'm going to give you one more, and then I'm going to let you go on. So Catherine says they are burned substances that come from that earth that take a long time to replace. They
Yep.
also release carbon when burned.
Yep.
All right, so go. I'm giving answers.
You guys are a sharp group.
Mm-hmm.
Absolutely. That's what fossil fuels are. And they were made from living matter, whether it's animals or plants that died a long time ago. They're not fossils in the same way that, because that's rock, but these are fossil fuels, and they are not renewable at the rate that we use them, because they take millions and millions of years to make. So once you use them, they're done. But they are a source for carbon and carbon, whether it's all forms of carbon and mostly carbon dioxide. So absolutely, you guys got it. So we're all there. So you know, what do we do to change the carbon cycle? How do we change the carbon cycle? We, people. How do people change the carbon cycle? So what do we do?
This is Grace reporting from the chat box. So now your answer. So the answer is, what do we as humans do that affects how carbon moves in the cycle, right? So you're looking to get from the kids, what are some of the things that we do that affect this carbon cycle? How do we either add or take carbon away? So let's see. Sonia says by adding or taking away carbon. And so Sonia, we're looking for a specific example. What's one way that maybe we contribute carbon dioxide to that atmosphere, or one way we take it away? So Michelle says if we stop burning fossil fuels, then we're releasing less into the atmosphere. What can you think of something that you do in your everyday life that might release carbon dioxide into the atmosphere? Can you think of an answer to that question? I'm just based on the chat, kind of refining it a little bit. So Texas says just our breathing.
That's true.
And Ada and Carl are saying that using a car contributes. Sloan is saying the same thing. Sonia is saying driving cars. A lot of people are saying driving cars contributes.
Yep, that's one.
Mm-hmm.
Yeah, that's definitely one.
Anyone else before I check out? Anything else?
I'm going to give you a hint. Do you know what this is? What is that?
Coal and fire. Sloan is saying coal. Donna's saying coal.
It. Yep. Burning coal is a huge source of carbon dioxide production by us. And I'll give you the last one. It's actually gas. Natural gas. So Oil and natural gas sometimes are come together, but they're not the same thing. But gases, natural gas is another one. So, but those are the big ones. Those are human activities that are changing the carbon cycle from the way it was before we were, about a couple hundred years ago. And so that's what we're going to be looking at, is how the carbon cycle is changing, and as a result, the warming of the planet occurs. So, Tom, you want to walk us through this fun graphic? This is an important one.
Sure. Sure. Thanks, Frank. This is Tom. What we're looking at in this graphic right here is the level, or how much carbon dioxide has been in our atmosphere going back 800,000 years. Now, I know me and Frank are a lot older than you, but this is even a heck of a lot older than us. It's a very, very long period of time. And you can see going back 800,000 years, we're looking through ice ages here. We're looking through multiple different ice age periods and warm periods in between. And you can see the amount of carbon dioxide in the atmosphere has changed in the past. Back when humans weren't around, you can see it's gone up and it's gone down. When it's been down, it usually relates to colder periods. When it's been higher, it relates to warmer periods. And you can see where we are right now is much, much higher than the amount of carbon dioxide that we've ever had in our atmosphere going back at least 800,000 years. And a lot of that is because these previous periods we're looking at a natural carbon cycle. These natural things are adding carbon dioxide to the atmosphere and naturally taking them out of the atmosphere. Right now, we're doing something that's kind of outside that natural cycle, and that's taking all of those fossil fuels and burning them, and then releasing more and more carbon dioxide in the atmosphere. It's like it's like having a water balloon fight with somebody, and you all thought you had the exact same amount of water balloons, but except someone had some fossil water balloons, were able to grab them, and now they have a lot more water balloons than you do. It's kind of what we've been doing. We've been dipping into all of this really, really old carbon. Now, you might be thinking, how can scientists, especially scientists at NOAA, because we do this sort of thing, how do we know what the levels of the carbon dioxide gas in our atmosphere were 800,000 years ago? Because we weren't around back then.
Yeah, Tom, I set you up for that, and then I forgot to put it in here, so you're gonna have to walk them through that one.
Sure. I mean, we can maybe. I'm curious, Grace. You want to ask? Does anyone have maybe any ideas how we might be able to tell how much carbon dioxide was in our atmosphere that long ago?
Okay, so this is Grace reporting from the chat box. So Tom's question is, how do we know how much carbon dioxide there was in the atmosphere 800,000 years ago? Connor and Daniel say we do estimations, but how do we do estimations? Is there something we can look at, or something we can, Wyatt's got the answer. Wyatt, I'm gonna hold on 1 second and see if anyone else comes up with it. So Wyatt says ice cores, or how you can. We've got we've got some other answers, but I'm going to go with Wyatt's.
Sure.
So that's you.
Thanks, Grayson. Thanks, Wyatt. Ice cores. What the heck is an ice core? Right? What is an ice core? So an ice core is scientists, some of which work at NOAA or are funded through NOAA, can go to these really, really big ice sheets in Greenland or even in Antarctica, and then they drill a small hole really, really far into the ice. And the cool thing with the way ice forms in Greenland and in Antarctica is that when it forms, it traps air within the ice. So, and you can actually count the years by how deep or how big that ice core is. So you have this really, really long ice core, and then you can find little trapped bubbles of air within it. So you can look back 800,000 years in ice across Greenland and Antarctica, and certain places that we know have been ice covered for that long of a period of time. There are other things that we could do this too. Doesn't it just have to be an ice core? We could have something called a sediment core, which is basically, think of it like mud, but like a lot of mud that's been slowly added to year after year after year. And we could drill deep down within that and find out little things that can tell us what the atmosphere was like hundreds of thousands of years ago. Well, great job. Great answers, everybody. Great job, Wyatt.
Awesome. And thank you, Tom. So we're gonna dig into this because what's happened in the Earth, and remember those answers we had from before. what puts carbon dioxide into the air and what removes it is what we're looking at here. And really what's important is the balance between those. If the amount that's being added is more than the amount that's being removed, the level goes up. If the amount that is being removed is greater than the amount that's being added, then the level goes down. And it's that up and down is really what's important to us, because that's where the temperature comes from. The temperature of the Earth, if we had no carbon dioxide in the atmosphere, we'd have a frozen ball of ice, and life would not be so nice. But because we have some, it's able to keep us warm. The problem we're having now is because of what we're doing, we're putting way more in, and it's getting to be too much because the temperatures are really starting to rise, and it's causing challenges in lots of important ways. So I made a video. I'm just going to give you, I'm going to try this out, and I'm going to go full screen. So I made this yesterday, and it's my own demonstration of why does the water, in this case, but it's the carbon dioxide, go up and down. So what this starting at is 170, it's called parts per million, is back when we had ice ages. And it was so low because so much had been drawn out of the atmosphere that it was so cold that you could actually build huge ice sheets. So Tom, if I remember right, you grew up on Long Island. That was, did I get that right?
That is right.
And right north of Long Island was a humongous ice sheet covering it. And then things started, more carbon dioxide was coming back into the atmosphere, starting to warm up, and you start getting more and more carbon dioxide building in the atmosphere. And this is, 100,000 years ago, 200,000 years, 300,000. The air is, continuing to build more carbon dioxide until it gets to a spot why it starts to slow down, and then things start removing it. So here's what I did. I removed carbon dioxide from the atmosphere. And what that's doing is, remember, what removes carbon dioxide from the atmosphere is plant activities, the ocean takes it down, other things like that. And it starts removing carbon dioxide and putting it away from the atmosphere into rocks, marshes, plants, and starts creating carbon locked away from the atmosphere, and then the carbon dioxide drops down, and then temperature drops down again. It went back and forth, we know, for a very long time. We went back between ice age and then warm, and then ice age and then warm. And so then when that starts shutting off, then they start going up. But notice, I just turned on the water level. And this is to note us, and starting to find these wonderful things back at the beginning of the Industrial Revolution called coal, and then ultimately oil and natural gas. And we started using them, and a lot of benefits happened from using them. But you start seeing it going up a little bit more. And then it's starting to go up over 300 parts per million. And then it's starting to go up more. And remember that graph where it went way up really fast? That's what we're doing right now. And the reason why I chose the bucket height I did was because when it fills up too much, we have too much carbon dioxide in the air, you start having problems. And so the bucket overtops. That's the idea here. And the reason why I did that, and I noticed you guys probably getting distracted by those two dogs. The orange one is George for you, Tom. The other one's Rico. But this is now where we are, where we have so much water in the bucket or carbon dioxide in the air that we are starting to get into trouble. And a lot of the warmth and the stronger storms and the bigger droughts and the bigger fires is because the warming of the atmosphere. But if we increase the things that remove carbon dioxide out of the air, and I just told my son Lucas to turn off the water, so you'll see it in just a second, you can actually bring the carbon dioxide level down. But you don't want to bring it down too much, because then you don't want to go back to an ice age. But this is the grand thing that we're people all over the planet are trying to do, is to figure out how to get the right level of carbon dioxide in the air so it doesn't get too hot or too cold. Make sense? Hopefully that demonstration worked, but that's kind of what I was playing with yesterday. There we go. So any questions about that? Hope that was fast. I don't know, Tom, did I miss any points in that one, or was that good?
Yeah, that was good. It's all about kind of this give and take of our atmosphere. It's kind of like a sweet spot in the middle when it comes to carbon dioxide and greenhouse gases in the atmosphere. So there's a natural cycle that kind of plays. It takes them away and adds them, it takes them away, but we've kind of been adding more. So this idea of getting back down, there's two ways of doing that, right? Either you can stop releasing greenhouse gases, or you could also make it go down by increasing the amount of things that remove carbon dioxide gas from the atmosphere. So there's two different ways of going about it, as Frank showed in that really neat bucket experiment.
So Grace, do we have any questions that came from that?
All right, this is Grace reporting from the chat box. So let's see. Sonia is asking, what is an example of taking away carbon dioxide? So can you remind us what takes carbon dioxide out of the atmosphere?
Absolutely. So while we are having challenges with big wildfires out west, forests actually at the age of the forest remove carbon a lot or not as much as they used to. So one of the solutions that people are working on is growing forests. Over thousands of years, we've removed a lot of forests, whether they're the big kinds like the Brazilian rainforest or the forests in wherever you are in the United States, depending on where you are. Enhancing those forests is one way to do this. Another one that we've looking at NOAA is something called blue carbon. Marshes and mangroves and seagrasses and kelp forests all remove carbon from the atmosphere through living processes. Those are also strengthening them will increase, and then the big one is soil. How we use soil, if we use it really, really well, it actually it pulls huge amounts of carbon out of the air, but it really depends on how we use for farming and agriculture or managing lands. All of those will remove carbon through natural processes. There are some crazy ideas, and I don't mean that in a pejorative, it's just like it's hard to imagine how it's going to work. But like there are people working on big vacuum cleaners that actually would just suck it out and create rock or something else from the air. I haven't seen it work yet, but there are people working on it. We'll see if the grand carbon vacuums are coming. But plants are really effective at doing this.
Yeah, and so this is Grace reporting from the chat box. And I will say one thing that I always like to say whenever I'm talking to students or in classrooms is you are the future. You are our scientists, our engineers, our designers, everything. So, think outside the box. You are now educated to know what the problem is, and you can get the tools to come up with solutions. So I look forward to seeing what some of you come up with. But we did get a really interesting question from Juan that I think is worth you talking about, because I think a lot of times people wonder this. Is carbon dioxide healthy for our lungs? Is it unhealthy to breathe carbon dioxide?
Ooh, that's an interesting question. It depends, with most thing, it depends on the amount. So the amount of carbon dioxide that's in your lungs, absolutely it matters. So you don't want to have too much. I'll give you an easy example of that. I used to love swimming underwater for long, long distances. I was known to be one of the best. The reason why I could do it was, if you've ever swam underwater, the reason why you want to go up to the surface is because your body feels and senses too much carbon dioxide building up in your lungs. And it tells you, you got to get up and get it out of your lung. I would just ignore it and swim a lot longer. But that's yes, too much carbon dioxide is a problem. There's lots of other examples of that. But the stuff we're talking about right now it doesn't meet that threshold yet. So that's not going to be a problem, even if we had 900 parts per million, which is double what we have right now, basically. Still wouldn't be strong enough, but it's a great question.
Great. Thank you for that answer. Very comprehensive. And So Clark is asking, how fast does the soil work? I think a lot of us are familiar with, some of the other ways we've talked about, but how fast is that process?
Mm. So, Tom, you mind if I take a shot at this one?
Sure, go for it.
So, I don't know the answer to that question. It's a great one. But there are people who are studying this exact question. And Grace, I appreciate your point from before, and I'd like to make just one little build on what you said. There are so many wonderful people working on solutions that you probably are just thinking that, that's popped into your mind. And what about this? And soil is definitely one of them. There are people all over the country and the world working on how do you do that as fast as possible. I'm not one of those experts, but there are a lot of them. If a key word you want to look into this is something called regenerative agriculture. If you use that word in whatever search on the internet you want, regenerative agriculture is where you're using practices on farms to pull carbon down into the soil to make the soil stronger, but also to remove it from the atmosphere. You're doing both things simultaneously. And I think that I remember seeing some people studying this, and the amount of carbon that's down there through these processes is huge. It's a lot bigger than you think. It's tons of carbon dioxide that's turned into organic carbon material in soils. But the rate, that's a really good question, and I don't know the answer. I believe when you don't know, you should answer it that way.
So I will chime in, Grace, from the chat box here, that my stock response to that, so I'm so glad that somebody did ask a question, is if we don't know the answers, which even as experts, we don't know everything, it's a good thing to research. So I would encourage you to look that up, because that was not you, Frank, but I'm sorry.
It's all good.
I would encourage Clark to look that up. We have about 5 minutes left, or about 3 minutes left, but I have two interesting questions. I can't remember how many slides you have left. So do we have time for two more questions, or?
Sure. Yeah, well, let's
Okay.
do it.
All right. So the two,
Well,
go ahead.
you know what? Actually, let's. I'm going to leave it on this one, and then let's see. The questions are really important, so it's more important that we get there. But just the last point here is that because we're releasing these fossil fuels, we at NOAA are measuring every day, multiple times a day. Sorry, Tom, I'm going to just take this one to wrap us up. We're measuring carefully how much carbon dioxide is, and we've been measuring it for a very long time. And the real question is that line going to continue going up, or is it going to flatten out and maybe start coming back down so it doesn't warm up as much? And that's what we've been doing. So let's get to those questions.
Great. I don't mean to pull you away from the slide, and I think that one of the questions that will come at the end is what the up and down is. But one great question that came from Carl and Ada is, do other planets have carbon on them? So is this process happening on other planets?
Tom, you want to do that, or you want me to?
I can take that one. Yeah, there's gases on all the planets, depending on where they're located. One good example of this is Venus. Venus is just a little bit closer to us to the sun, but its temperature is a lot hotter than the hottest temperatures in the solar system. And a big reason for that is that the atmosphere of Venus is just chock full of these greenhouse gases, of carbon dioxide, of methane, and it's unbelievably hot because of that. So yeah, a lot of different planets across the atmosphere, because the cool thing about the universe is that it's really made up of all kind of the same stuff, just in different amounts, like all different recipes when you're making up a planet and its atmosphere. So like, yeah, the different planets have all of these gases just in different amounts.
Great, thank you. That is a great answer. And then I'm going to ask two that I think are related. So Michelle asks, what is smog? And Sonia asks, do the clouds look different in the sky when there's too much carbon dioxide in the air? So I think people often confuse smog with what we're talking about. So if you could address both of those, that would be great.
Tom, you want to do smog?
Sure.
Or you can do both.
Smog is a combination of two words. The SM part is smoke, and the OG part is fog. You combine them together and you get smog, and that's where the word comes from. So smoke is made up of kind of tiny particles of things that got burnt that are in the air that reflect the sunlight and kind of look all gross, for lack of a better word. But that's different than carbon dioxide. So carbon dioxide is something that we can't see and we can't smell necessarily. So the stuff that like smoke, though, if you've ever been outside and it's been really smoky, been by a fire before, and you see the smoke coming up, you can smell that. There's a smell. When you go camping and you come back and your clothes all smell like smoke, that's what's going on. But that smoke, when it gets released into the atmosphere, can interact with clouds, can interact with all these different things and kind of form smog, and smog can kind of settle over a city. Now, smog has its own kind of bad impacts on us as humans that are a little bit different than carbon dioxide. We had a really great question about how much carbon dioxide is it bad for you in your body. Well, breathing in a lot of smoke is bad for you. So that's why it can be dangerous to be outside, especially during these wildfires out on the West Coast when there's high levels of smoke and smog in the atmosphere, because that stuff can really hurt your lungs if you breathe in too much of it. They're different from each other, and they kind of form in different ways.
And Tom, the other question there about the changing of clouds, this is actually one of my favorite questions. Do you mind if I take this one?
By all means.
Awesome. So one thing that's important to know is as you change the way the heating of the Earth, one of the big questions we are still working on, and I used to work at NASA for a long time, and this is one of the things we were working on there, is as you change the warming of the planet, do the clouds change? And if the clouds change, the way energy from the sun comes down and interacts with the Earth changes. And so this is still, I think, there's a lot of unknowns that we're still working on. We definitely know how the clouds work and where they are, but what we don't know is exactly how they will in the future based on how the Earth changes. And so the kinds of clouds and where they are and what seasons they show up, that's an unknown for some of us. And that's why we use a lot of satellites to study this. But we don't only need satellites. There's a lot of other instruments used to study clouds. And sometimes I used to work with my students to study clouds from the ground to help validate and really give satellites senses of what is actually being seen from the ground. Sometimes it's easier to do it from the ground than it is to do it from the sky. So it's a great question, and that's why we're continuing to research these questions. Now I'm going to close this out here, Grace, with we gave you some resources in the website where you connected this for your families and yourselves. This is one of my favorite games about the carbon cycle. We had a carbon scientist at NOAA said this is the most important idea that people just don't get, is how the carbon cycle changes from before humans were using industrial processes and after. And this is a video about it. The game is there. And so we just want to let you know that. And then Tom, you want to talk about this event coming up?
Sure. Tomorrow we have another kind of fun thing that you all can register for called Climate Alive. It's the every full moon watch party put on by Ocean Today, the NOAA's National Ocean Service. And I'll be one of the experts there talking about all of the wild weather and climate extremes that we've been seeing across the planet over the last month or two. So you can make sure you can go to that and you should make sure you can register for it. It's completely free at 4 o'clock tomorrow.
And as somebody who works with Tom on a weekly basis, I get this kind of information. You do not want to miss it. If you love this topic, I really encourage you going there, because there's been some really crazy weather going on in the last while, and Tom is one of the best at helping you understand what that is. So I encourage you.
I'll be talking a lot about smoke and smog tomorrow, if that interests you.
Yeah.
Excellent. I know we're out of time, but I really think this question warrants asking. So if you could each give a quick answer to this. Patty asks, so this is Grace from the chat box, as single individuals, what would be the best or biggest thing that we can do from our side to reduce or contribute low amounts of carbon dioxide?
Sure. Great question. Tom, you want to start and I'll finish?
Sure. That's a really good question. I have to think about it for a second.
I'll have a, go.
If you have an answer, Frank,
Oh,
you
I've
should
got an answer.
go for it,
Okay.
Frank.
Sorry for those who people are signing. We're a little on top of each other. So here's my answer to that. Individual actions are important, but the things that really add up are really the most important. So the like if we were able to say not use gasoline cars anymore, all of us, or we got all our energy for electricity in our homes and what's powering our computers to be able to talk and see each other um, not from fossil fuel sources. Those are the big things that we need to do together. It's the things we do together that actually add up the fastest. We still do them individually, but what I do or you do is important, but it's what we do together that is the absolute most important. And so the good news is a lot of us across our country are doing these things, and most people don't know. So the good news is we're on our way. The less good news is we've got a lot more to go. And remember that bucket. That bucket has got to not just stop getting more. Unfortunately, in the atmosphere, that bucket goes much taller than what I showed in my demonstration. And we want to make sure that that does not happen because it's not going to work out very well for all of us and the ecosystems we rely on. Tom, what do you think?
Frank covered a lot. I'm going to add one aspect more of that, and this may seem simple, but I think it's really important, and that's talking about it.
Yeah.
It's just talking about it. Asking your community, your school, your community groups, your churches, your schools, your governments, whatever it may be. It's just to talk about it more. You'll find out an easy way of kind of creating community uh, is by just being able to talk about it. You'll find a lot of people who want to do something similar to you, and you can come up with ideas, and then you can find out through NOAA, through climate.gov, we have examples of communities across the country who are taking action and doing all sorts of different things to kind of reduce our emissions of greenhouse gases. And you can see what they're doing. And the community aspect is so important. And I always say the first way to get that going is to talk about it.
I agree.
Great. I'm going to thank Frank and Tom, you guys. It was it was neat to see the bucket challenge and really see it sort of happen in front of us. And thank you for all the information. We appreciate you being part of NOAA Live. I'll tell everybody that next Wednesday, our NOAA Live for next week is going to be on weather balloons. So the National Weather Service will be, we'll have someone talking about weather balloons. But thank you so much. Appreciate everyone taking time. I know with school back in session that time is precious. So we appreciate you being part of NOAA Live with us, and we will see you either at the full moon watch party tomorrow or we'll see you next week. So thank you very much, and I guess I'll see you later.